Imagine a universe inside the tiniest speck of matter. Before the 20th century, our idea of the atom was surprisingly sweet. Think dessert. J.J. Thomson, after discovering the electron, proposed the plum pudding model. Picture a soft, positive sphere with tiny negative electrons scattered like raisins in a pudding. The positive pudding balanced the negative electrons, making the atom neutral. This model explained neutrality and the presence of electrons, painting atoms as soft, squishy spheres. If you shot something through it, it would pass through easily, like a BB through fog. This was the accepted view, taught everywhere. The atom was thought to be a calm, predictable, mushy place, but science thrives on challenge. In Manchester, England, Ernest Rutherford and his team were about to test this model. They planned to fire tiny bullets into this atomic pudding. What they found would shatter the old model. The atom's inner universe was about to be revealed as far stranger than anyone imagined. The stage was set for a groundbreaking experiment. The world was about to learn that atoms weren't just soft clouds, they were about to discover something dense and powerful at the heart of matter. The story of the atom was about to change forever. The next chapter would redefine our understanding of the universe. The experiment was ready to begin, and nothing would ever be the same. Enter Ernest Rutherford, Nobel laureate and master experimenter. At Manchester, he led Hans Geiger and Ernest Marsden on a mission to probe the atom. Their plan was simple: shoot something at atoms and see what happens. The gun was a radioactive element like radium, which emitted alpha particles, tiny, fast, positively charged projectiles. These alpha particles would be their bullets. The target? Gold foil, hammered so thin it was just a few hundred atoms thick. Gold's malleability made it perfect for this delicate task. The goal let alpha particles hit only one atom as they passed through. To detect the invisible, they used a circular screen coated with zinc sulfide. When an alpha particle hit, it produced a tiny flash of light. Geiger and Marsden sat in darkness counting these flashes, mapping the unseen. Hour after hour they charted the invisible world. The setup was elegant, the approach direct. They were about to uncover the atom's secrets, one flash at a time. This experiment would test the very core of atomic theory. The results would change science forever. The gold foil was in place. The countdown to discovery had begun. Step into the dark Manchester lab, 1909. A lead box held radium, emitting a focused beam of alpha particles. The beam targeted a nearly invisible gold foil, just atoms thick. According to the plum pudding model, alpha particles should pass through easily. Surrounding the foil was a movable detector, a screen that flashed when hit by alpha particles. Geiger and Marsden watched for these flashes, mapping where particles landed. They measured straight paths, small deflections, and even checked for the unexpected. Every flash was a clue to the atom's structure. They were about to witness the invisible world in action. What did they expect? The plum pudding model predicted alpha particles would fly straight through the gold foil. The atom's positive charge was thought to be spread out, offering little resistance. Most particles should hit the screen directly behind the foil. A few might be nudged slightly, but large deflections were considered impossible. The idea of a particle bouncing back was unthinkable. Like a bowling ball rebounding off tissue paper. The experiment was supposed to confirm the old model, nothing more. The experiment began. Flashes appeared as expected. Most alpha particles passing straight through. A few deflected at small angles, matching predictions. But Rutherford urged them to check for large-angle scattering. Geiger and Marsden moved the detector to extreme angles, even behind the source. Suddenly they saw flashes where none should be. Some alpha particles were bouncing back, an impossible result. Only about 1 in 8,000 did this, but it was undeniable. Rutherford was stunned, comparing it to firing a cannon at tissue paper and having it bounce back. The plum pudding model couldn't explain this. The atom's positive charge and mass had to be concentrated in a tiny, dense center. The atom wasn't a soft pudding, it had a hard core. This was the moment that shattered old ideas. The experiment revealed a new atomic reality. The nucleus had been discovered. Science would never look at the atom the same way again. The results demanded a new atomic model. In 1911, Rutherford proposed the nuclear atom, mostly empty space, with a tiny, dense, positively charged nucleus at the center. If an atom were a stadium, the nucleus would be a marble at its center. Most alpha particles passed through the emptiness, a few were deflected by the powerful nucleus. Rare direct hits bounced back, revealing the nucleus's immense density. This discovery transformed science. Matter was mostly empty, with dense cores. Nuclear physics was born, shifting focus to the atom's heart. New questions arose. What holds the nucleus together? Why don't electrons collapse into it? Rutherford's model wasn't perfect, but it set the stage for quantum mechanics and the Bohr model. The gold foil experiment unlocked the atomic nucleus. It turned the atom from a fluffy pudding into a miniature solar system. This triumph of experiment and open-mindedness changed our understanding of everything from energy to the stars. The atom's true nature had finally been revealed.